Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you understand how to apply concepts of mechanical vibrations to a simple pendulum. So a simple pendulum is kind of like its name implies. It's basically a mass on the end of a string, kind of oscillating back and forth. So in this example, imagine that somebody has taken this mass, displaced it to this angle. Now the theta sub m stands for theta max, right? And released it from rest. Then this object would undergo motion like this, back and forth. Okay. So this picture that I'm going to call picture 1, the object is at rest, it's not moving. But I'm going to compare that to picture 2, where this is a generic theta, if you will. It's not at 0 or 90 or an endpoint or something like this. And what we're going to do is we're going to write and solve the equations of motion for this object. And I'm going to do so using the work energy theorem. Right? If I write out the work energy theorem, the potential energy 1 plus kinetic energy 1 plus work equals PE2 plus KE2. Okay, PE1 is all potential, is a gravitational potential energy, and that's it. There's no springs associated with this problem at all. And if we use this as our datum, the distance we need is this distance, the vertical one there. The hypotenuse is basically L. That distance that we need is adjacent to the theta max. So the potential energy term is minus mg L cosine of theta max. Okay. No kinetic energy at term at 1 because it's not moving. As usual, there's no work term here because there's no external forces adding energy to or taking energy away from the system. So the entire left-hand side of that equation is written out. Okay, the PE2 term. So in a very similar sense, the PE2 term can be written minus mgl cosine theta. Now it might seem like these are the same, but they're not. This theta is a constant. It's the maximum theta in the problem. This theta is a variable. It is changing with time. As usual, I didn't quite leave myself enough room here. Okay. Now, at position 2, we also have a kinetic energy. Now, you can actually write the kinetic energy a couple different ways. Right? Method number 1, we could write it 1/2 mv squared. And we'll do a little manipulating here in just a moment. Or we could write it like, we could treat it like an object rotating and write it 1/2 I omega squared. And for the I, we can use ml squared, the moment of inertia of a point mass about some sort of axis. Right? So we could write our kinetic energy like that. Now, regardless of how you write the kinetic energy, theta is our variable of interest right here, right? This one is okay because the omega there is d theta dt. If we write our kinetic energy as 1/2 mv squared, we have to do something about that. Now, this distance along this path right here, remember, that's an arc length. And it's equal to the radius of curvature, which is basically the length, times theta. And then if you differentiate this, this becomes a v, and this becomes a d theta dt. And I'm going to, because I'm tired of writing d theta dt and dx dt and stuff like that, I'm going to use the shorthand notation theta dot. Again, the dot is just shorthand for d theta dt. So you'll notice that if you sub L theta dot in for the v, you end up with 1/2 L squared theta dot squared, which again is the same as right here. 1/2 ml squared theta dot squared, because that's what the angular velocity is, right? It is the rate at which theta changes, so theta dot. So this equation is now going to become minus mg, oh, you know what? We don't need the masses. We might as well divide those out. So minus GL cosine of theta max, I don't feel like writing it all out, equals minus GL cosine theta plus 1/2 L squared. Need to make myself a little room here. Sorry about that. Times theta dot squared. Now, I'm going to just make sure I did that right. 1/2 ml squared theta dot squared. 1/2 ml squared theta dot squared. The mass divided out. Yep, we're good. Okay. Now, to introduce time information, we hit this thing with a time derivative. I like to call it the time derivative hammer. ddt of the following. This entire term, these are all constants, so their time derivative is 0. Okay, looking right here, this is all constant. And the derivative of cosine theta is minus sine theta d theta dt. So that derivative ends up being GL sine theta theta dot. Okay. Plus, now we look here. Now this is all constant, but we have to differentiate this, and that's theta dot squared. So that thing's time derivative, let's see, is L squared theta dot and then theta double dot. You have to differentiate that again. You have to chain rule it. Okay. Now you'll notice this equation is starting to look like, you know, a second derivative plus something equals 0. Right? So we're happy about that. Also notice the theta dots go away. So I'm going to rewrite this equation, second derivative first with a 1 in front of it. That's standard form. So that's going to be theta double dot plus G over L sine theta equals 0, I believe. Divided everything by L squared. And the theta dots divided out. Yep. Okay. Okay, so now we're really, really close. Now, hopefully you've watched my videos on how to solve things like y double prime plus a constant times y equals 0. It's pretty easy. You have sinusoidal, or, you know, sines and cosines for solution. This thing isn't quite like that, though. This isn't theta, it's sine theta. Right? This differential equation is what's called a nonlinear differential equation, meaning truck piles more math, basically. But what we're going to do is we're going to make a simplifying assumption, and we're going to restrict our answer to small thetas. And hopefully we remember from calculus that if theta is small, then sine theta is approximately equal to theta. So that allows us to write this theta double dot plus G over L times theta equals 0. And now we're happy. All right, need to get rid of a whole bunch of this stuff, though. Okay, so again, now we're happy. Because now we recognize, okay, this thing has to have trig solutions. So theta needs to look like A sine omega t plus C cosine omega t. All right. Then, like a lot of these problems, we can use this condition that when t is equal to 0, this object's not moving yet. So theta dot is equal to 0. And in the interest of time, I'm going to leave this to an exercise to the viewer to go through and time differentiate this, and what you should conclude is that A equals 0. So we're just going to keep this part, the c cosine of omega t. Okay, now we're going to start working with this. We're going to need the second derivative. All right, so the first derivative is going to be minus c omega sine omega t. Second derivative is going to be minus c omega squared cosine omega t. Now this goes here, and this goes here. It's quite a bit of writing. And hopefully you've watched enough of these videos, you got a decent handle on this. By factoring, you're going to find that the omega is the square root of g over L. All right, so the solution now, we got theta equals a constant times the sine of root g over L times t. Now we can apply that at t equals 0. Theta is theta max, whatever that is. Oops, and I made one little glitch here. It wasn't the sine we were keeping, it was the cosine. My bad. Okay. When we make this substitution, we get that c is equal to theta max. Oops, I'm writing q's there. Theta max cosine of root g over L times t. So this one has a cosine type of solution, just like the last one I looked at. And again, to get the period of motion, when this cycles through 2 pi, then the cosine function goes through one cycle, meaning that this object will do this and back again. So that means that root g over L times the period is equal to 2 pi. Pretty easy to solve that. So the period is 2 pi root L over g. And the frequency is 1 over the period. So this should be pretty easy to test. We'll probably do this in class. We'll probably make ourselves, say, maybe a 2-meter pendulum and check its period against our math here. I hope that this helps. Have a great day.